Good morning and a warm welcome to everyone. I am Luis Santos, a software engineer from the research and innovation team at UbiWare, and I'm pleased to host this session as a member of the 60 Project Consortium. This is the third webinar we are hosting within the framework of 60 Twins activities, a project that is being funded by the Smart Network and Services Joint Undertaking, otherwise known as SNSJU, under the European Horizon Europe Research and Innovation Programme. To provide a very brief introduction, our role as a String BSNS JU project is to research potential new technologies that can enable the network architecture of future 6G systems. With novel 6G applications, new challenges emerge that the higher throughput and lower latency of 5G is simply not enough to accomplish. From fully autonomous connected systems, such as teleoperated driving and vehicle-to-X communication scenarios, to smart city use cases with multiple domain infrastructures, each producing domain-specific data representations. All of this supported by a physical network that spans from public and private cloud data centers down to edge nodes and even user devices. Providing network services and applications to users in these environments with 6G application requirements is still a challenge that is being studied by initiatives like us. Today's agenda focuses on the topics of digital twins and AI, and how these enablers can help us address some of the challenges in building intelligent, adaptive, and trustworthy network for the 6G future. This webinar features the representation of another call to StreamB project with 6G Cloud. While 6G Twin covers the foundations for design, implementation, and validation of AI-native 6G architectures, focusing on the incorporation of the network digital twin as an end-to-end core mechanism to enable real-time network optimization and management, 6G Cloud investigates the key technologies to enable an AI-native service-based 6G network architecture, focusing on a cloud-friendly system that integrates cloud resources from multiple stakeholders, seamlessly providing network functions from different 6G network segments on top of the whole cloud continuum. To give a brief introduction to the four great speakers that have given their time to be here today and present some of their respective project achievements, firstly, from the 6G Twin side, we have from the side of the Luxembourg Institute of Science and Technology, we have Sebastian Fay, project coordinator of the 6G Twin project and head of the DISCO research group at LIST. From the University of Bourgogne, we have Iskander Zelagi, a PhD student focused on researching AI models and how they are used within the context of the 6G Twin NDT. From the 6G Cloud project, from the side of VTT Research Center, Technical Research Center of Finland, we have Tao Chen, project coordinator of the 6G Cloud project, and principal scientist and senior project manager at VTT. And last but certainly not least, from the National Center for Scientific Research Demokritos, we have Nikos Dimitriou, technical coordinator of the 6G Cloud project and tenured research member of the Institute of Informatics and Telecommunications at NCSRD. With this not so brief welcome and introductions out of the way, the agenda for today will cover two presentations from the side of each project. Firstly, from the side of 6G Twin, we'll have a presentation on the 6G Twin vision by Sebastian Fay, followed by a presentation of some results achieved by the project on multi-objective route optimization for teleoperated driving, presented by Iskander Zelagi. From the side of 6G Cloud, we will have a presentation on the overall 6G Cloud service-oriented architecture by Tao Chen, followed by a presentation on the role of network digital twins within the 6G Cloud framework by Nikos Dimitriou. Finally, we'll conclude this webinar with a small panel discussion where we can intersect the ideas between these two projects, how they tackle some unique challenges, and what are some shared research topics for the development of 6G networks. That's all from my side. Thank you for your attention, and I will now pass to the first speaker. Please, Sebastian, the floor is yours.
Thank you, Luis. I will just share the screen. Just tell me if you see the slides. That would be a first good step, probably.
Right now it's, oh, perfect. We can see the slides.
There. Okay, good. So thank you very much for the introduction. Welcome to everyone again to this new webinar. Thank you to our guests from 6G Cloud. It's super nice to have this webinar session today together with you. I hope we will have some constructive discussion. So on my side, I will not spend too much time. I think I will just recap a bit what we are doing in 6G Twin, what's the vision of the project as you introduced, Luis. So the idea is just to set up the baseline, and then my colleague Iskander will go into the details of some ongoing activities. So again, 6G Twin. What is 6G Twin? I guess it's important to start a bit with this kind of picture. So as Luis already mentioned, 6G Twin has been funded by the Smart Network and Services Joint Undertaking from the European Commission. And so there you can see quite a lot of projects that have already been funded. And if you have a look at their website, you will probably see quite a few tools that are extremely useful when it comes to understanding, the current technologies that are under development at the European Commission level. And if you see among all these projects, there are at least 30% of them who are declaring using digital twin technologies. So it's quite huge. And this is exactly what we are tackling in 6G Twin. The main issue we see today, and this was the case, of course, when we launched the project, is that most of these projects are basically using heterogeneous approaches. There is no standardized definition of what is a network digital twin. So how to use, let's say, a kind of sandbox to test, optimize different solutions before applying them into the live network. There are quite a lot of approaches that are developed by the literature, but so far we are still far from having a common understanding and definition, and this is precisely what do we want to make progress on in this project. So advancing network digital twin technologies. So that's really our objective, to try to design, implement, and validate what we call an AI native reference architecture, targeting the future mobile networks, and that specifically integrates the network digital twin concept as its core mechanism. So the project started in January 2 years ago. We are in the last year of the project. That's also why I'm very happy, to have this kind of webinar, because we can open to some interesting discussions, collaborations with partners, or even with the audience. The budget is about 4 million euro, and as it was mentioned, it's a Stream B project, so from SNSGU, so more focusing on system architecture aspects. I will just try to introduce the overall architecture of the project, the concept we have, without going into too many details. I think we can also leave you with some very recent references that have been published. So this functional architecture that I'm going to present has been accepted for publication a few days ago, and it will be released soon. I guess it's already even available through our Zenodo community. So the idea, right from the beginning of the project, we followed the recommendation from ITUT on digital twinning, which defines a high-level architecture for defining for using a digital twin in these network domains. So here what you can see is extremely easy. You have the physical network made of many different, the usual suspects, let's say, many different elements, ranging from the user equipment to the core network, radio access network, etc. And then on the other side, you have, some humans or some machines that want to deploy and to use applications. So on our side, we have two main applications there. We have teleoperated driving, and we have another application which is more related to energy savings. So the entire idea of, a digital twin is basically to provide a tool that can, on top of the physical network, sense data, sense the needs, think and plan some actions, and then act in real time on the physical network. So we are not talking about a totally disconnected simulation environment as it was done 20 years ago. We are really talking about a sandbox that can collect data in real time, use this data, like optimize things, try to predict what could happen, maybe playing with different scenarios, and then when the most intelligent choice is made, acting directly in the reality by through the network controllers, and changing the parameters that need to be changed. So that's useful, for instance, for capacity planning. That's useful for optimizing in real time the energy consumption of a network. That's useful for maximizing the quality of service for some applications. That's why we are typically using this concept. So that's the big picture of the functional architecture we have proposed, at least in a way that can be understood through this kind of presentation. So there you see many different colors, and I will just go very quickly through them. So the first color, well, let's say the first block in blue is where the data models are defined, and where the database, let's say, the databases are populated. So here the idea, as I was telling before, is to collect data from the reality. The challenge we might have here is that, well, most of the time you will end up with heterogeneous data sets. So you need a way to harmonize these data sets, to store them in a coherent way, independently on what happens on the physical network. So there we are relying on some smart data models, on some let's say models that allow us to end up with a unified data model repository, and a unified data repository. So there you can see some plots and a video of one of the main tool we are using in the project for that, which is called GreyCat. It's let's say a framework that has been built here in Luxembourg, which is open source, so you can rely on it. And the idea is really to use that to build a graph-based, let's say, representation of the physical network. So again, we will not go into the details because I guess Iskander will have more insights there, but this is really where the models are defined. And then we distinguish two types of models: the basic models, which are more the real world representation, and then the functional models, which are the ones to optimize this real world representation. Then we have an AI training and optimizer toolbox where we can pre-train models, so that then we get a bit of time. So there we can come, by the way, with some. I mean, this is a toolbox that can be used for let's say populating the functional models we are considering here. So all in this project, we are considering three types of models. So we have the trained AI models. We have the algorithms, to train and optimize the models. So more what is here in this yellow toolbox. And then we have simulation models, which are more for long-term prediction. These are things, let's say, that are not necessarily real time. So here we can use this kind of simulation tools that are well known. So here, for instance, it's a co-simulation between Sumo, so a mobility simulator, Omnet plus, which is a network simulator, and then we also have a 3D interface, so that we can visualize what happens, what could happen potentially. So the idea of this simulation toolbox is again to run long-term simulations, and we are also considering that in the project. So that's really the beauty of that kind of architecture, to have the possibility to let's say to calculate, to predict, to launch different forms of models depending on the need in the reality. So we have real-time stuff, we have things that are more long-term, and all this is orchestrated by this box in purple, which directly translates the needs from the network applications, and also coordinate the data feeds, let's say, coming from the reality. So again, we'll not go into too many details, but just to mention that this is basically about the project. We are developing technology components that are directly attached to these different boxes here. And if you are curious about that, well, we already have quite a few publications. We already released, I guess, more than 1,000 pages. So this does not translate. I mean, does not mean that the quality is there, but well, but believe me, you should definitely discover the many deliverables we already produced and the publications that come with them. So in total, 10 technology components translating directly into that. And so that's the baseline I was mentioning before from ITOT, which has been released already in 2022. That's the baseline we are using there for this architecture. We extended also some of the existing work so that we have also an understanding on the lifecycle management of all these entities. So just to show that. And in the project, we are focusing on two main demonstrators. So as I was saying, one on teleoperated driving and one on energy efficiency. So teleoperated driving, the idea there is more to predict. So use the digital twin as a way to anticipate what could happen in terms of quality of service, when we want to, let's say, teleoperate a vehicle, or when an autonomous vehicle, for instance, has to go from one point to another. This is directly linked with some of the experiments we are doing here, for instance, in Luxembourg. So there we are building some synergies. We are also, again, very open to collaborate. We all know that mobility is a huge challenge in Europe. In Luxembourg, it's even worse given the size of the country and the cross-border areas. So they are very, very happy to collaborate. And so the second demonstrator is more about energy savings. There, the idea is to adapt the network conditions in real time. So there again, if you want more details, it's not the target of this presentation, but just to show you an overview. We are more towards the end of the project. So the next step is to release the federated simulation framework and models. So the orange box I was showing before, the idea is to share as much as possible with the community so that you can also reuse these components for you, right, for your own needs. And that should come quite soon. That's it from my side. I hope we are still on time. Yeah.
Thank you, Sebastian, for the great presentation. Just a quick reminder for the viewers in the chat. We have opened the QA chat box so that you can ask your burning questions to the presenters. And if we have time during the scheduled panel discussion, we can address some of them. Right. So on to the next point in the agenda. I will pass the token over to Iskander for the next presentation.
Hello everyone, thank you for your presentations. Let me try to share my screen. Is this visible?
Yes.
Okay, so hello everyone. For this part of the presentation, we will talk about multi-objective route optimization via Dueling DQN for teleoperated driving, which will serve as a functional model for the 6G twin use case of teleoperated driving. So to start off, I'll tell you a little bit about this presentation and how it's gonna go to give you an idea. We'll start off by talking about our motivation and context to what we are working at, then the problem formulation that we try to work on, as well as our proposed solution and how that work can be integrated into the 6G twin, and then followed by the experimentation and evaluation of our approach, and finally with a short conclusion. So starting off with our motivation and context, in other words, why teleoperated driving needs 6G. To understand that, we first have to understand what teleoperated driving is. It basically is when a remote operator controls a vehicle via a 6G link, requiring continuous reliable connectivity, where any disruption equals safety risk and there's no fallback allowed. And why we need 6G in this In this case, is because the current network capabilities are not enough to deliver such a use case. And for that, we have 6G that it promises sub-ms latency, ultra-high reliability, network slicing and edge computing support, and many other capabilities. For this case, we have our core problem when we talk about the teleoperated driving, is that those driving decisions that the operator is going to make are going to depend both on traffic and network states. And here comes the problem. It's that classical routing algorithms cannot take into consideration live QoS metrics, which gets us into our motivation, which is the need to make something for a joint mobility plus communication optimization. So how does that really fall in with the and 6G Twin is a project that has one of its use cases to deliver teleoperated driving. To be able to see it simply, we have again a remote operator that controls the vehicle through 6G uplink, which will probably send video, sensor data, control signals in real time, which will need more capabilities than we currently have in 5G. And we need to know that network degradation. So the route must account for both network coverage gaps and QoS variations along the path. How does that fall exactly with the 6G twin again? But let's be a little bit more technical. We'll explain this later anyway. This is just to give a broad idea. First, we have to understand what an NDT is, or a network digital twin, which is a real-time visual replica of our physical network that will enable us to monitor, analyze, predict, and optimize through AI-enhanced models. In the case of the 6G twin, we have two types of models: basic models and functional models. The basic models are the virtual representations of network elements and topologies, as where the functional ones are AI-based models that enable analysis and decision making. And as you might have guessed, our focus is to develop one of those functional models for teleoperated driving scenarios within this NDT framework of the 6G Twin project. So, what are we solving exactly here? We saw our problem as that there's a safety requirement for the teleoperated driving, where it has strict requirements for the efficiency and safety, and they depend heavily on reliable network connectivity and performance. And the current limitations is that the current routing approaches that we have fail to consider the real-time network conditions and the variations that may happen, which may create potential service disruptions. And for that, our objective is to create a vehicle route optimization model that will take into consideration multiple objectives, which are the distance, bandwidth, and latency. So we decided to solve this with reinforcement learning. Why we chose reinforcement learning exactly? Because it is more effective for dealing with dynamic environments more than the traditional algorithms that we talked about. On top of that, it fits in naturally as part of the 6G twin architecture. To explain our solution a little bit, our RL-based approach, and when we talk about RL, we need to define our Markov decision process. To put simply, we have an agent that will interact with an environment by making actions and having observations and rewards from that environment, which will allow the agent, to keep going with actions until reaching what it wants to reach. Here, our environment is a graph of a city in France called Nevers, where we had our roads as edges and their intersections as nodes, with the varying network metrics in time. The state got some vehicle positions, some real-time network conditions, and the destination coordinates, which will be explained a little bit later. later. The action is choosing the next node, and the reward is a weighted combination between the distance, bandwidth, and latency. We'll talk about the agent later, as well as to explain why we chose the Dueling DQN architecture. So this shows the environments better and explains the problem even further. We have the real map of the city that we transformed into a clustered graph, as we can see here, where nodes are intersections and edges are road segments, and taking into consideration that the latency and bandwidth are dynamic and change over time. What we basically want to do is, at any point of this map here, we can start, for example, from any point, and we have a destination at any other point, and our agent will try to map the way from node to node until arriving to our destination. So as I said, the agent architecture here is a dueling DQN with two streams, where one of them is the state value and the other one is the action advantage. These two is that because the first one estimates how good of a position we are in at any given moment, and the other one tells us which action to make at that position. Next up, we're going to talk about the 6G twin integration, or how our model fits in with that architecture. Basically, our whole contribution to be seen from a, if we may say, to see the and balanced path the vehicle can take, and then we have the 6G twin architecture, which makes this the deployment of this model natural and efficient. How is that happening? It's that our Dueling DQN model is stored as a functional model within the twin. We'll see how in a bit. On top of that, we have flexible training. To explain this even further, we can see the architecture that Sebastian just presented. The DDQN model, for example, or our route optimization model can be saved here as a functional model, where it can be trained in another block of this architecture, either by real data or simulated data. And why do we do it this way exactly? It's because it enables a lot of it opens new doors for us that can be explained right here. Allow us to simulate how different routing strategies perform under varying network conditions without actually needing to deploy the changes on the real network. Needless to say, that will save us a lot of time and energy in the real world. On top of that, we have the predictive support, where we can anticipate network degradation along a path that we already planned, and proactively recommend alternatives before issues arise, which where is the dynamic reality, or the dynamic form of the real world is, and that we can take that into consideration and make the best actions. And finally, we have the service evaluation, where we can use the twin as a testbed to assess how different network slices or edge deployment strategies impact performance. To evaluate our work, we did some experiments, and you can see the results here, where we had a combined metric between distance and KPI respect rates, which basically means what percentage of the whole road we have our KPIs respected in the project. And what I mean by KPIs here is that it's the minimum to allow for a teleoperated driving experience to happen, which in our case are a latency less than 35 milliseconds and a bandwidth or uplink throughput higher than 20 megabits per second. And as we can see here, our RL agent outperforms all the classical algorithms that take into consideration just one of those metrics. You can also see it here not in a merged way, but each one on its own. You can see again that our RL agent is the closest to the best case that we want to allow for such a use case as teleoperated driving to happen in the 6G twin. finally, to conclude what we achieved here and what we talked about, this work demonstrates reinforcement learning's capabilities to intelligently balance competing physical network objectives. At the same time, these findings establish a robust foundation for network routing in teleoperated driving systems, showcasing that 6G Twin's compatibility with the use case is a key to enable it, which explains why all of this works together so well, explaining the big image, in other words. And finally, we see this as something that paves the way for new research in next generation 6G networks and connected autonomous mobility. Thank you, everyone, and I'll leave the stage for the others that come after me.
Thank you, Iskander. Very insightful. Now switching gears, we move towards the 6G cloud perspective, following up with Tao's presentation, whenever you are ready.
Okay, so let's check. Can you see my screen?
We can.
Yeah. Is it in the full screen mode or not?
It is not sharing the presentation. Oh, it is sharing now. Sorry.
Okay. Just stop sharing. Let me do it again. Okay. Okay. Okay.
Perfect.
So nice to be here to present our 6G cloud architecture. So my name is Hao Chen, and I'm project coordinator of this project. And also, I'm working with TT. So what is a 6G cloud? So this is a SNSJU 6G project that we are dedicated on the AI native and also cloud friendly this 6G system architecture. All those are built on top of the cloud continuum. And that means we deal with 6G architecture and also we deal with the cloud infrastructure. So this project, we have 12 partners. So from the 8 countries. So it's start from 2024, same period as the 6G Twin project. So now in this presentation, I focus on our architectural design aspect, and also our technical manager, Nikos, will cover the digital twin part and also the AML framework. So why we deal with this cloud system? So just give you a just brief overview about this cloud landscape nowadays that in the telecom systems. So you see that so the cloud system has already used in our daily life. Everybody used the cloud system, this cloud service that from one application or other application. So we know this cloud, central cloud, that's the cloud concept that everybody have a common understanding. But you also will see that the cloud already moved to the central part to the regional cloud, and also to the edge. That is in the promising of the buildings or network operators. But now even the move to the factory, and this promise that where the base station are installed, and also to the this devices that use equipment we talk about in 5G 6G domain. So for this use equipment, since it's not anymore just like a mobile phone, but also have robots, also vehicles and drones, and there are not of capacity there. So could install also the application. So you see that if you put all together, that cloud is everywhere. But how about our 6G systems and how we can leverage this cloud infrastructure to make a more flexible system, and also more importantly is to how to say suitable for the different service. So you see the evolution of the cloud also in the cellular system from 5G, 4G, and to 5G. And in the 4G system that is already 15 years ago, right, when they deployed, so it's only limited implementation on the cloud. That is use the virtual machine. That virtual machine means that each virtual machine has a guest operating system on top of the physical machine. So that is not effective because there's a lot of overhead to install also each guest machine that's in virtual machine. So we move to the 5G and we have see the progress of the cellular system. At the same time, also the fast progress of the cloud system. Right? So in the 5G area, so it's not anymore only used for virtual machine, but also they use the contain as a service. So that means they don't need to use the guest operating system in each contain. So there could be a contain that has also fixed this network function implemented, or they can use a serverless implementation that for one certain network functions. That means only when needed and they can implement it into the not to the cloud system. So that's more flexible. So that's we see in 5G. So if you see in 6G, because 5G is not pure cloud native design. Even they can put this DU, CU, this aggregation in the cloud. But for 6G, we see two cloud native system should arise to take advantage of this cloud system. Right? So that means the system architecture need to changes, and also this cloud native features and also cloud automations, also cloud resource should be used in 6G system. So 6G system provides this connectivity for the application. Itself should also utilize the cloud infrastructure to implement its system. Okay, so what is the point to involve the 6G to cloud native? So we see that at least in 5G, the core network has already used this cloud native design. We call the service-based architecture. Right? So, but in the radio access network side, so they still use the traditional way. They use this reference point architecture design. So this is not very cloud friendly. Right? Because in this design, so each component you see here, DU or CU as one component in the network, and they need to have defined an interface between each component, and also it's a point-to-point link. For instance, DU has a point-to-point link to the CU this use plane, and then this is very specific. So if you see that if CU want to connect to the core network, so they also need a new interface to define. So this is not very cloud friendly, and also that's cannot leverage the full power of this cloud implementation. So we see the motivation to move design of this 6G network to bring the 6G, this service-based architecture to the radio network. So in that case, we can have an end-to-end service-based architecture, can fully leverage this cloud implementation. So what this service-based architecture means here? So the service means here is not the service to the end user, but a service so that the network functions as a service, or AI as a service, or digital twin as a service. So we define those service as kind of the application or network function. So we use the same service-based interface to connect them to each other. So this is take these ideas from this cloud application microservice-based concept there. So we try to bring that into the 6G design. So what is the advantage for that? Certainly, we can use this very flexible implementation, because each one is a service. So we can implement the one service as one part of data function, and we can use this CI/CD approach, right? Just continuous integration and continuous deploying the approach, and to make this this network development that's more flexible. And also we can easy to deploy this network because it use cloud. That cloud can have a scalability when we deploy a larger system, and also easy for integration, and also good for the integration with the different Windows solution, because each is defined a service. So if you follow the same interface and also APIs, and then different parts should work for each other. And also, as I mentioned, this AI and this digital twin also could be a service, and could also support this integration, use the same architecture. Right? So the advantage of this service-based approach compared to this 5G design, this reference point architecture, is that they use the interface, same service interface for different network functions. So that means one interface can apply for all or many network functions, and also network function provide a set of API, and also can be really shared with other network functions. It's easy to implement this kind of control application type to you already see in the whole run. Let's make this reference point architecture. They have to define each interface. Each interface they have defined the same procedure protocol. So that's at least make a unify of this interface and make it easy for design for the future network evolution. Okay, so if you see that 6G architecture, if we put into this service-based design, so this is, and also we bring cloud infrastructure as a underlay infrastructure to support it. So it's not as simple as you just bring the service-based design there in the network side. You also need to manage a different resource, because the cloud resource, they have different cloud, and how to manage resource for cloud to give to certain network functions or certain network is not an easy task. For that, in this 6G cloud project, so we bring several frameworks to manage that. One framework is this cloud continuum framework. So it's to manage the underlayer cloud infrastructure. And also we bring a management and orchestration framework to manage not only the cloud resource, but also the network resource, and have the coordination together. And then we use the AMM framework, also the digital twin to bring this intelligence and also automations into the network. So now bring all this together. We just have this architecture here. So it looks, the first look, it looks complicated, but if you see it closely, you can divide it into 3 framework plus in the middle that this service-based 6G network. So you see that in the middle is we talk about is the different 6G network instance that it could be based this run part and also core network part, and implement in the different cloud, and so there could be also many these kind of 6G networks that implement in the same cloud infrastructure. We just need the same management framework and also a cloud framework to manage it. So for that, on the top you see this MOF we call here is management and orchestration framework. That's provide a unified framework to manage this cloud resource and this network resource. So more details were given in the following slides. And also at the bottom you see the cloud part. So cloud system is managed by CCF. So that means there are different cloud system: a central cloud, this regional cloud, and also the edge cloud, right? So for each cloud, we have to define which resource could be used by certain network service instance, and also there are some kind of requirement regarding that where to put these network functions regarding this latency and also other use case use requirement. So this CCF should handle this kind of requirement and give the right resource that's to the network slicing, the network service. And then we see the AMM framework. Nikos will provide more detail. So it's also to provide a unified framework and can support also the need for different AI for the operation, right? So there could be AI in the MOF, or AI in the CCF, or AI in the run functions. So let's see that what this service-based design on the run side that looks like. So this is about overview. That of course this is a simplified view about future 6G network. So 6G network have this qualitative side. We assume it will continue to use this service-based design from 5G, but for the 5G side, for the run side, so we see the evolution, right? So for that part, we see the data plan. So this will follow the point-to-point design, because that's need very high throughput and the reliability. But on top, on the control plan, so we see that when the cloud is used, and then literally will evolve into this service-based architecture. So we assume that there's a certain way to exchange the data or message that on this architecture we call the service bus or message bus here. So you see some control plan functions as from 5G can implement that as a service on this message bus, so they can exchange information on the bus. But also there's new functions can define as all put into this service bus. For instance, AI function, we have this AIF is the AI functions on top, and also exposure network functions we can also link to the bus, and they can link to the third party. So that means we open this service that's to the third party applications, and they can use the certain mechanism to also to interact with the network function or control framework inside the network. And also we have this NAPS concept. That means this kind of new control logic can be defined, and this kind of programmability can introduce also into the system. So if we put all together, just from this 6G architecture point of view, that we see use this service-based architecture, so we can have this more flexibility to combine different network functions together based on need of the use requirement, and it's more flexible to implement new functions and new services to support use cases. Okay, so then let's move to the MOF management and orchestration framework. So the MOF is a unified framework that we hear, but for the implementation, it could be a distributed management framework. So if you see that we're talking about this 6G network, that is a network service in the middle here, and on top for each network, this 6G network instance, that we have one of this network service director. Is one of the management entity that for each this 6G network service. Right? So for each for this network slice, that this the director, you see the service orchestration is here, and also they have their own this business support system for charging, billing, and also the operating system for this fault and also configuration management. So the idea is they have their own independent control of the resource, right? For the network function chain, and also orchestrator to see how to manage and implement this network functions for this specific network. So there could be many. That could be many. Just because if you see that the cloud system is we include basically from the cloud, central cloud to edge cloud. So there could be thousands of the network can be managed by this MOF, right? But since the resource is shared with the cloud, and we need also some more centralized service orchestrator also to coordinate the resource in different network slice instance. So we have this master service orchestrator in the middle, and also we have this global business support system, global operating system that on the top, and as we say that this is use the cloud infrastructure, and so that the network functions could be some kind of say that imaging that already stored in the in some database that can be instanced that based on need. So we have also an asset repository that include this network slice, the network service template, and also the this policy and the service level agreement, the definitions here. So and also this morph also talk with the cloud system through this cloud continuum framework on the bottom. Right? So yeah, so if you see that for the important part for manage the cloud resource, we have this cloud continuum framework here on top. So this framework connect to the data center and to manage and to negotiate and manage also the cloud resource from different data center or different places, even in the edge, right? The edge is not in the data center, but it still also could be managed by the same framework. So, so certainly they need some database to have a global view about all this kind of data topology and data center topology, and also for the requirement, also keep the requirement from the network itself, right? Because network is implemented on the cloud. But the important concept here also is developed in 6G cloud is this resource partition, right? Because the resource partition means the cloud resource partition. That means different network service or network implementation. So when they need to use cloud resource, they cannot, not to say they can use any resource in any network, right? Any cloud, because that's not a realistic. So you have to give a constraint that which subset of the cloud resource can be used by this particular network service. So then in that case, the service current, so latency or other service KPI can be guaranteed, and at the same time you can make sure the security of the other issues is not violated. So that's for that service resource partition, we introduced several functions here to manage it. So this includes resource partition creator and also data center aggregation engine, and also some database to keep that information dynamically to reflect the reality of the network status and also cloud status. And also, since this system, the building block looks here is just several blocks, but is manage a very large and complicated cloud system. It's a heterogeneous cloud system. So we also need to do the predictions of the performance, and also to do anomaly detections, and also the resilience estimation. So we have also defined the building blocks and the functions here to really forecast the resource consumptions and to make the system operate smoothly, and importantly also the dedicated engine to manage the whole system, like this the CCF manager, and also this security agent and portal to manage the whole framework, and also to make the integration with the morph. So with this morph and the CCF, and also later on we will also mention this AMF in the other presentation by Nikos. So when we put all together, we bring this whole 6G cloud solutions. So here is one of the implementation we see here. So we have this from the 6G network side. We have the bubble run system here, provide also their implementation on the cloud, and with this system we make an extension to bring the service bus that's on top, as you see here on the top. So this service bus, we use Kafka in this version to implement the service bus, and also the different network functions can connect here to flexibly combine and for a more complete network functions for different users. Right? And then for the morph, and we have the right side to have the implementation here. Use the Kamada implementation for the morph, and also for the CCF. Also, we have also different open source tools and show here to implement. So the idea is, of course, to combine here and to test in our proof of concept. So some concept, also some some demo and then maybe show that in our next presentation. So just now, this is just some overview about our architectural design, also details about our framework. So in summary, our framework, so in 6G Cloud, we defined one 6G architecture, use a service-based design, and also we defined the 3 framework, that is cloud continuum framework, management orchestration framework, also AML framework to support this 6G network implementation. So for the digital twin part, that we have also digital twin part implemented in many places in the system, but mainly to use digital twin combined with AML framework to support the AI model training validations, and also to make the estimation for the decision before we deploy that functions that into the network. So for that, this is the summary for the architecture part. So now I'd like to hand over to Nikos for the next part.
Thank you, Tao. It's great that we can have 2 different project perspectives on the same topic. To conclude the set of presentations, as Tao mentioned, we now move over to Nikos, and we see the inputs from the side of the AI/MLF. Yes. The floor is yours.
Yes, thank you. Let me just share my screen. Okay, I guess you can also see it in full screen mode.
Yes.
Yes. Okay, so it's very nice, first of all, to be in this webinar. Many thanks first to 6G Twin for organizing this. And also, I'm very happy to present highlights of the work that we have been doing within the 6G Cloud Consortium with all the different partners with whom we collaborate very nicely over the last period. First of all, okay, the objective will be to discuss a little bit about the AI/ML framework that was mentioned by Tao in the previous presentation. So AI/MLF is actually located here. As explained before by Tao, we have a very sophisticated management and orchestration framework, and also a very sophisticated cloud continuum framework in order to build this network service that is end-to-end, encompassing all different elements from a RAN and core network, and also from the different network functions. So the question is, how can we actually have an intelligent way of optimizing all the different things that have to be optimized within these detailed frameworks? And this is the actual mission of the AI/MLF, which actually provides AI/ML models in order to serve different parts of the architecture as AI as a service, let's say, mode, providing analytics optimization, intelligent control functions and functionalities, and also assisting AI/MLF is we have the network digital twin here to actually provide assistance where necessary, because we don't claim to have a full network digital twin of the whole architecture. This is not something that we can support anyway at this stage. So in terms of the functional AI/MLF architecture, this is a more detailed, a little bit view of AI/MLF. You can see here that we have all the different elements of model storage, model learning, training. We have 3 different services within AI/MLF. This is a training service in order to receive data, training data, and provide this AI/ML training. Also, inference service to use AI/ML models pre-trained in order to perform inference, and also performance monitoring, because things change, to make sure that we also always have, let's say, the best possible solution for the right problem at hand. And what I'll show is shown here is that we see within the architecture the AI/MLF in a distributed mode, serving specific places of the architecture, providing this AI/ML service where necessary. So with this respect, the network digital twin is considered, as also discussed before in the previous presentations, as a virtual emulation or simulation collection of models interacting with the physical network. This is very important in order to have this closed loop data-driven network automation beyond the traditional network simulation. So in that sense, in order to have this comprehensive, as we say here, cognitive plane for the 6G cloud architecture, we see ways with which we can have representation of the physical network at different parts in order to accelerate and assist AI/ML training. Also, we had the same initial steps as the 6G Twin, leveraging the framework from ITU and also from IETF in order to have this the design of the 6G cloud version of the network digital twin that involves, of course, data repository. Data is important, identifying different data sources and identifying data sets that could be used either to support emulation or to see how emulation can support these data sets for actual AI/ML training. Of course, the NDT engine that provides this network modeling and also identifying perhaps different entities that could collaborate with each other. And of course, the entity management for orchestrating the whole procedure. So in that sense, of course, we have developed a specific methodology for developing a digital twins. We also, as I said, see the digital twin as a way to have a magnifying lens within the architecture to show exactly the problem that we're trying to solve and to see how we can exploit the data from this part of the architecture, either from core, RAN, or both, and also to identify the actual cloud resources that are involved in this in order to assist the AI/ML model training that should be performed. In that sense, I just briefly will show a little bit one implementation that we have here also in Democritus, where we have the data repository using specific tools such as Prometheus, the data engine considering the URAN SIM for the RAN and also the Open5GS for the core part of the network, and also the orchestration of the entity, which is used with the slice management tool that we have, which is Katana. And also the visualization, again, where we have Grafana. I don't want to go through this slide in detail, but I just want to show that we're looking at multiple data types, multiple data set types from the different parts of the network, either the RAN or the core network, and also the computing resources that we have to consider, plus also the end-to-end network service characteristic parameters and performance, let's say, metrics. So we're trying to see how we can identify and collect different data for different problems that we would like to solve, and to see how we can exploit them also, perhaps also storing them and perhaps reusing them for other objectives as well. Now here I'll just, let me just also put this animation here, sort of animation, showing a little bit how we have this set up the physical network, which includes the elements that I showed before for testing and evaluation, and also depicting different metrics in that sense here. And also in the next slide, also the network digital twin of that scenario, where we have again specific ways to monitor the different performance metrics that are collected, and to see, first of all, at the first step, how we could match the actual, the physical and the network digital twin designs that we have developed. Now, in terms of the scenarios, I'll just briefly mention the 4 different scenarios that we are looking at. One of them is about traffic anomaly detection, considering DDoS attacks. So I guess this, I'm just showing here on this blueprint of the architecture, the actual things that we are focusing on for this NDT test. We see AI/ML based classification using LSTM classifiers to predict different attack types, as a TCP float, the UDP float, etc. And also we consider UE traffic from different UE sources. And then we try to see how we can use them for offline training and optimization of AI/ML, specific AI/ML models, to apply them again to the physical network. So we try to see a little bit this bi-directional data flow of information from the digital twin to the physical network, and again back to the physical network, the actual results, to see how we can have, let's say, a better performance in the real world. And this is also, we're trying to see this also in a network of network scenario where we can have multiple networks, either public or non-public networks, and perhaps flexibly changing among them according to specific conditions that are observed. The next scenario is related to multi-cell RAN traffic anomaly detection, where again we have these phases of training, inference, and also identifying alarms for anomaly detection. A specific model creation process has been developed, and also here you can see also the different tools that are being considered in order to develop the entity in that case. Again, also another scenario is related to interference detection in mission critical scenarios. So here we have the actual case where we have a specific institutional user, let's say police, fire department, etc. They want to respond to a specific case. There is a critical scenario that has to support with a wireless network, a reliable wireless network, specific requirements at hand. So how can we use, let's say, the 6 cloud architecture that has been already presented in order to flexibly either deploy a new private network to support such a scenario, or to improve, let's say, this network to be operating without any interference in order to make sure that we have, let's say, the required resilience. And for that, we have the actual use of different sources of data, either from emulated network or also from an actual simulated network in combination also with a physical network. And this is another scenario where we actually would like to see the overall logic that I showed you before in such a setup, as I said, for a specific scenario where we have near real-time, let's say, models that have to be trained. And then, okay, the last scenario is a little bit close to the first scenario that was also presented by 6G2N, where we talk about metaverse-enabled mobile networks, where we don't look at only transferring the actual network to be represented as a digital twin, but also specific elements of the physical environment around the network. So in that sense, we look at the element of the case of the actual nested digital twins or layered digital twin within a single twin platform to represent both network and non-network related elements of the physical architecture at hand. So this is a more ambitious scenario, let me say, but okay, this is also, it has a lot of interest here as well. Also, and you see, also there is a lot of interest within 3GPP as well. So, okay, I tried to give a concise coverage of the part of the entities within 6G Cloud. Thank you very much for your attendance, and looking forward for any questions or discussions. Thank you.
Thank you, Nikos. Thank you for being so succinct on time. And thank you again to all the speakers. In order to carry on the topics that have been discussed in these presentations, I would like to invite you all into this panel discussion, the final item of the agenda. I will start with some questions, and then I will move on to questions in the chat if there are any that are still open. I see that you have been responding to the questions that have been put there. So my first question is directed towards the 6G Twin project. Some standardization bodies like ITU, ETSI, and ISO have been moving towards filling the current gap, that is a reference architecture for network digital twins. Does the 6G Twin project view this as an exploitation goal? And if so, how?
Well, maybe I can provide the first answer, and then I see Iskander already has hand raised. Yeah, so of course it's an objective for the project. We come from this Stream V call, so again we are not targeting. I mean the level of research we are doing is quite. Let's say conceptual. So if you take the technology readiness levels, which qualify well the maturity of a technology, we are basically targeting TRL 4, 5 maximum. So meaning that of course we have to contribute to the scientific community, publish papers and so on. But one of the clear objectives there is to contribute to standardization bodies and try to influence them as much as possible. So we are active there, I would say. The architecture we have built is well itself based on a recommendation from ITUT, so the International Telecommunication Union, and yeah, we have ongoing interactions with ETSI, with some working groups there. So yeah, I would say it's a clear objective. Iskander, probably you want to complement this?
Thank you, Sebastian. I totally agree with what he said. Well, in that case, I just want to add a little something. 6G Twin does not see this as just a research outcome, this whole architecture and standardization, but as a primary exploitation goal. And to look at the different standardization bodies, they often lack, well, they have some high-level digital twin definitions, but they often lack the 6G specific AI hooks, which the projects would like to work on and aim to bridge that gap in this sense.
Okay, nice. Thank you for your clarification. Um, so my second question would then be towards the 6G Cloud project. As more and more automation mechanisms are offloaded to AI/ML algorithms, this also increases the demand on the network. How does the AI/ML framework specifically optimize for this growing number of requests, some of which might have real-time or near real-time requirements?
Okay, let me address first, provide an answer to that. Okay, I agree. Of course, we agree that we have, as we said, we have a framework and an architecture that involves a lot, huge amounts of data all over the architecture, both in the RAN and the core, and also heterogeneous data, perhaps with different time granularities, also with different sort of volumes. And definitely AI model training and pre-processing are very demanding procedures in many cases. So what we're trying to see within the architecture is to have also to this AI MLF architecture can be considered both in terms of centralized or decentralized fashions. In the decentralized fashion, we try to see the actual use of data where it actually originates, not to transfer huge amounts of data across the network. And also we try to see the actual training, inference, and performance monitoring pipelines to be running locally. Of course, we also see cases where we can have some sort of pre-processing of data and filtering of data if we need to have them in a hierarchical way processed closer and let's say in a more centralized location. And also the architecture enables the use of federated learning in order to make use of the results from different, let's say, training cases and points, and also transfer learning, where you can use the results of learning of one AML training for another, let's say, similar application. So the architecture is open to have, let's say, all the different combinations of decentralization according, of course, to the requirements. Okay, and probably as more delay intolerant are you, the more, let's say, close to the edge this processing has to be made. Thank you from my side.
Okay, so I want to also add that so we have this framework designed that for architecture, but that framework doesn't mean that all framework is just a single entity, centralized framework. It's a distributed framework. That means the AI can also implement in a distributed way, and also for the AI we have this AI framework, but the AI model is pushed to the place they are going to run that is integrated with data functions. So in that case, is also that it depends on the need for that data functions. AI is customized for that functions, and also the load to load is also distributed in the network. And for the real time and the non-real time, that certainly there's different control loops that in the network. So at least if you see in our system architecture that we have at least 3 different control loops. That for the cloud we have 1 control loops there, and for the morph we have 1 control loops, and is more for morph I think is more on the more larger scale control loops. And also for the 6G network itself, we have network function control functions there. That is more like a near real time control loops there. So different control loops for AI is used a different AI model or AI algorithm there. So but is really AI to use to solve the real problems in different places. So it's not just like a general AI framework.
Thank you for your clarification. Now, I will broaden the scope of the questions towards both projects. As we've seen, both 6G Twin and 6G Cloud place a heavy importance elements in the management and orchestration of networks. From the side of 6G Twin, we have the NDT Mono layer, and from the side of 6G Cloud, we have the management and orchestration framework. How do you see traditional management and orchestration frameworks evolving to incorporate digital twins as decision makers rather than just simulation tools?
Who starts? Iskander, do you want to give a right? Yeah.
I may start, Sebastian.
Okay, please. I should start. Okay. Yeah. So I guess the idea is to have a flexible approach, right? So we will not replace anything that exists today, but the idea of this methodological twin manual, so the one we introduced in the projects, the local box. If you remember my presentation, the idea is to have something quite transverse, and I guess at the end of the day, the way we will implement it really depends on the use cases. So I mean, I very much liked one comment, that was made, I guess, one of the slides related to 6G Cloud. So I see so many papers, trying to cover everything with this network digital twin concept, but it's impossible. So we cannot build, everything, right? We cannot. We have to make choices. So whatever we are doing, at least in 6G Twin, with our MVP framework. I mean, we know that in the reality, it's use case oriented. So we have to define tangible use cases, be it related to a specific sector or a specific function to optimize, and then pick the right functionalities and the right building blocks to solve a specific challenge. So yeah, I guess the answer is that. So whatever we are bringing on our side, it should be something flexible on top of the existing interfaces, network interfaces.
Okay,
yeah, please.
Yeah, okay. I think for the digital twin part, is in my view, digital twin certainly is important tools in the network. Is used to make some validation of the decisions, and also digital twin can use to generate the data, right? This could use to be trained AI or for other purpose. For the digital digital twin, it is in 6G Cloud that we see the digital twin used for AI/ML framework, and we use that for generate data and for validate AI model if we push into the right place to do the work. So and for the implementation side, right? So if you see you mentioned that this morph is a complicated system, and then how to even integrate that digital twin that in the system. So this we are deal with this service-based or service-oriented architecture. So we see this how to say, there's a functions, or even the morph, there are also different functions. They can treat as a service, right? So different service, for instance, this management service and that management service can combine to form the morph functions. And digital twin is part of the service. This also play in a way on demand, that when you need this kind of digital twin to play the role and to make some decisions or as a reference to some part, you can integrate, plug in this digital twin part into the work. So when we don't need it, then we just remove maybe that plug in that way, and then they make it this flexible way to implement.
Would any speaker like to add some?
I just wanted to add that, of course, one important thing is to make sure, we need to have, first of all, synchronization between the physical and the network digital twin to make sure that the network digital twin solves the right problem. And this synchronization is served by the service-based architecture that we have, where you can have the communication of the different elements, and also to the ability to, as I said, have targeted twins where the actual problem solving has to be made in the specific area of the architecture, and also to allow the use of specific bidirectional mechanisms to have the interaction between the NDT and the physical network. Because if we have standalone simulations only in a silo mode, this many cases may not serve the actual network problem that we're trying to solve. It's not an easy solution. It has a lot of issues and a lot of abstractions perhaps have to be made, but of course these are the principles that we have to follow.
Very true. Sorry, go ahead, Iskander.
Thank you, Louis. One more thing I would like to add to really understand the thing that is different from just having simulation tools. Here we want to jump from just reactive management to predictive governance over the network. And what we mean by that is that instead of just reacting to things that may happen in the network, we will be the primary decision makers. And by we, I mean, of course, the network digital twin.
And following up on this, for my next question then, I see that both the digital twin is a crucial system in the 60 twin and 60 cloud architecture. So how do you see the scalable deployment of such a complex system across different network domains with different requirements, such as edge, regional, and central clouds?
Maybe we can make a link also with the last, I see one question in the chat. Which
the last question in chat, yes.
Yeah, from George, who is basically asking, where do you see hyperscalers' roles in the future of mobile networks? And could they influence or rather disrupt the usual standard telco network frameworks and designs? So for me, that's quite complex actually. If we could predict that, that could save a lot of time. But there are many different aspects. So I think the telco operators will still own, let's say, the spectrum, radio. They will be in charge of the regulatory aspects. And then the hyperscalers, well, clearly they can own the cloud platform, the AI tooling, the automation, the developer ecosystem. So I think the disruption is not, it's not about seeing telco operators disappearing. It's more that telco operators might risk becoming infrastructure providers over the long run, if they do not come with the necessary computing resources. But obviously, with this shift towards AI-based networking and the need for more and more, bigger and bigger data centers in this context, then we might have this kind of debates in the future. So having the telecom operators, which are more towards the management of end users, the infrastructure, and so on, and the hyperscalers capturing the intelligence and the service value. So that's quite a complex debate, but I guess this is the different models are being defined now. Just to comment on this, but I don't know if there is any reaction to that.
Okay, I have some comments on that questions. So I think this already happened. So if you see the all-run deployment, right, already in US, also in Japan, so this cloud system already played an important role to implement this all-run network. This is happening, but if you see how the hyperscaler played a role for the future mobile networks, so the cloud has different nature, right, compared to the traditional telecom system like 4G, 5G, because they normally don't need a standard to do the implementation, because they are just the hyperscaler. They implement some solutions that they just deploy it, right? So in that case, you cannot use like a 3GPP to define how his hyperscaler will behavior to implement these mobile networks. But of course, there's a need that, for instance, how the cloud system will be used in the mobile network. If you see all-run, they have all cloud, and they define already some kind of interface and the way to operate or deploy the resource that in the network. So in that sense, also in 3GPP, because 3GPP traditionally the cloud is not part of their system. They define interface, they define this radio network and also the cloud, but they don't define the cloud part. So if the hyperscale want to influence this mobile network, that means they may have to engage into some 3GP standardization. I think this is also happened that many hyperscalers they already engaged in 3GP, at least in certain working groups that, for instance, SA5 or other groups, and to see how they can make that influence.
Would any other speaker like to add any comment? Perfect. Then I'll move on to my final question. With the Data Act and the EU AI Act, there have been a lot of importance placed by the European Commission on trust, resilience, and explainability of AI mechanism. As 6G is headed towards a more and more AI-driven network, how are 6G Twin and 6G Cloud tackling this issue directly?
So quick question, because I see only 2 minutes remaining. So in 6G Twin, we of course we take that quite seriously, and I mean it all happens, when we collect the data from the real network to actually feed the digital twin itself. So there we are relying on an harmonization mechanism to first be sure that all the data types and the data sets can be understood by the entity. But then we are also relying on the notion of data spaces and smart data models, particularly, which are, let's say, kind of frameworks. This has been around for many different fields, like health, mobility, energy. And now we are bringing that for the telecom sector specifically. Thanks to these frameworks, we have concrete means, let's say, to define a governance model between who owns what, in terms of data. We have some privacy rules as well, and we can consider quite a lot of aspects, let's say, make the data collection routines of the project compatible with the regulations you mentioned. So that's the way we tackle this in the project. But I think we have a full deliverable dealing with that, and 2 deliverables dealing with secure data collection, and on the other side, the governance models and the way we apply this in the project. So once again, I really encourage all the audience to go to the deliverable webpage of the 6G Twin website to check that.
Okay, from a 6G Cloud point, also we are looking, we have in the AML framework specific provisions for, first of all, for explainability, having an explainable AI module to try to identify additional features for the AML models that are developed, and also to have more visibility in the actual model behavior, having also the human in the loop within this procedure. First of all, to enhance the trustworthiness, let's say, aspects of the AML architecture. And also we have a data integrity module in order to perform checks for accuracy, completeness, consistency, validity, and also security. So we look at such aspects as well, because as we said, apart from having, let's say, huge amounts of data that could be considered for exploiting in different parts of the architecture, definitely issues related to trustworthiness and also to security are very important.
Okay. And also remember that we, in the cloud system, we have this kind of partition concept that also applied to the data is integrated.
Perfect. So if there are not any more inputs, I would like to first thank all of the speakers for their time and for their great answers to these questions. I would also like to thank the audience for attending and for giving such good questions and interacting with the presentations. And I would like to invite you all to follow the project pages directly, both on LinkedIn, their project websites, and the Zonoro communities. And from our side, I think that's it. Thank you all for joining us, and have a great rest of the day.
Thank you.
Thank you very much. Thank you.
Thank you,
very
everyone.
much.
Thank you.
Thank you.
Bye bye.
Bye bye all. Bye bye.